Hello. So in this video, we're going to look at again another application of the diffusion equation. This diffusion equation is so kind of useful. So useful in this module because it kind of models all movement. Okay, anything which moves can basically be modelled by the diffusion equation. And we're going to look specifically at this thing called Fick's equation of diffusion. And it was Fick was actually he was a physicist about more than 100 years ago. This theory was kind of discovered. So it's sort of, it's a well-established theory. It's not anything new by any kind of modern standards at all. It's been around for a good 100 years or so. But basically what he did is at the moment we've just been considering one random walk. So in other words, in one dimension still. So we start at 0 and we can either move to the right or left. And it's just one person. It's just one person either moving to the right or left. But now what Fick decided to do is what happens if we have more than one equation. Because of course, if you're considering, for example, a herd of animals, for example, moving through a landscape, okay, you're trying to model how the animals are moving, you're never just going to model one. You're going to model lots of them because they're usually going to travel in packs or herds or whatever you want to call them, but a group of animals moving together. So effectively what we need is not just one random walk, but multiple random walks. And this is what Fick's equation was able to do. So instead of just having one random walk, we can have, say, 10,000 random walks, or 20,000, or 5,000, whatever, we can have more than one random walk. And effectively, how he did it was he considered the transport of matter. So basically, he said that matter. Let's suppose that matter is this, and it's moving in a direction x. So let's suppose it's moving in this direction. So it's moving in the x direction. So left and right. Okay. And he basically discovered that the flux. Now, flux is just flow. Flux is just another word for flow. Flux is just another word for flow. Okay, so it's just the flow of a material, for example. So left and right. It's just if you like, liquid is flowing along. Flowing along this. Matter is just like water is or a liquid is matter. So therefore, it can flow along this kind of tabletop. So it's talking about how the matter can flow effectively. So flux is just this, and we define it by Jx. This is the notation we give it. And basically what he decided is he said basically what Fick was able to discover was that the flux or the flow is proportional to the gradient of the concentration of matter. So in other words, so what this is basically saying is that as there's more matter, okay, it's the gradient of the concentration of matter. So the concentration of matter, let's call the concentration of matter C. So just how much matter you have. So basically what he said is that Jx is just proportional. It's just proportional to the gradient of this concentration as we move through this particular direction. So this rate of the rate of change of the concentration as we move through the material. Okay. So basically this is what he's saying is that basically Jx, the flux, the flow of the material, is proportional to the concentration of the matter, as the concentration of how much matter there is as we move through the material. Okay, so and the constant, obviously it's a bit like saying that y is proportional to x. Okay, well that's the same as y is equal to some constant times x, and the constant is actually minus d, and the d just corresponds to the diffusion. It corresponds to the diffusion, so how quickly the matter spreads out. So how quickly the matter spreads out along this table, for example, this surface, right? So this is basically what this is saying. This is Fick's equation or Fick's law. It's called. This is what's known as Fick's law. Fick's law. Okay. Now, for those of you that are really observant, I kind of snuck a minus sign in there. The reason why there's a minus sign in there is because that kind of shows that diffusion will always occur from a high to low gradient. Will always occur from high to low gradient. It's a bit like, I always think that, diffusion is kind of, you always want to move so that you're equally spread out, or particles always want to move so they're equally spread out. Okay, so they're always going to move from an area of high concentration to an area of low concentration. So they're always going to try and move to an area of high concentration to a low concentration, so that effectively we get kind of like an even distribution, more even distribution, rather than being sort of highly concentrated. It's a bit like, people want to move. Hello, so in this video we're going to kind of carry. Sorry about that. So yeah, basically, the the diffusion. So the whole idea is that you want to move. Say, I always think of it as moving from the city, which is very congested, to the countryside, where it's kind of very low, very few people. You want to move to the countryside. And that's all diffusion is. It's moving from an area of high concentration to an area of low concentration. And that's why that minus is in there, because it's moving from high to low. So if you like, it's moving from a high number to a lower number. So therefore, it's kind of decreasing, and that decreasing is represented by a minus. Okay, so that's kind of the logic behind that. Okay, so basically the whole idea is that we can use this to obtain what's known as Fick's equation of diffusion. And Fick's equation of diffusion basically says that the rate of change of the concentration of matter. So the rate of change now, this is how the concentration of matter changes over a direction x. You know, x was our direction, x was like our surface. This is what dc by dx meant in this equation, okay? But now what I'm saying is that it's dc by dt, so it's how fast the concentration of matter changes. So how fast, the matter spreads out, okay? And that is equal to the negative of my flux, so negative gradient of my flux, okay, just kind of, using that I can derive this, okay, or that is equal to the derivative with respect to x of this thing, because obviously I know what jx is, yeah, jx is in there, so therefore it's going to be, the derivative, so I just replace jx in here, so it's going to be, if I just leave the minus there, so it's going to be minus dc by dx, okay? Well, I've already got a minus here, and I've already got a minus here, so therefore I can just get rid of those minuses, and so therefore this is just the same. This is just exactly the same. So this is what's known as Fick's equation of diffusion, okay? Fick's equation of diffusion. Now, when this when this diffusion coefficient is constant, then basically this can be solved just subject to the condition that there were initially m particles concentrated in a particular area. So basically there would be m particles concentrated in a particular area. So m particles in a particular area, okay? And this particular area that we started, it's the area that we started with. So let's say x equals 0. So maybe if I draw this onto a line like this, so we start at x equals 0. So all of the particles effectively start at x equals 0 if d is constant. So in other words, it spreads out at a constant rate, okay? And so therefore what that says is that c, so the concentration at the point x at time 0, okay, is equal to, and this is just coming from, the Dirac delta initial conditions that we had before, it's just going to be given by m delta d x, because remember that the initial conditions that we had before with the probability that someone starting at x at 0 is just given by the Dirac delta function at x, okay? Well, now what I'm saying is that I've no longer just got one person. This was the case where we just had one. Now what I'm saying is I've got m different particles, or m different people, or m different species, whatever you want, or m different animals, whatever you want to say, okay? So I'm going to call it a concentration. Okay, so it's going to be a concentration, and it's just obviously going to be m times, because I've got m different animals, so it's going to be m times my Dirac delta function. Okay, so hopefully you can kind of see the logic behind where that comes from. And so therefore what I can say then is that if my probability was given by this, was given by 1 over square root of 4 pi dt, e to the minus x squared over 4 dt, then therefore now my concentration, so hopefully you can see the relationship between my concentration and this, it's effectively if my p was given by that, and my concentration is just going to be m times p. It's just going to be m times p, right? Because my Dirac delta function is equal to p. Let me try and show you. So yeah, let's try and get rid of this now. There we go. So if c equals m times my Dirac delta function, I'm just going to call it Dirac delta of x, okay? And if p is equal to my Dirac delta function of x, then therefore I can just replace Dirac delta function with p. Otherwise I can just say that my concentration is just going to be m times p. So in other words, my concentration now is just going to be m times all of this lot. So m times all of this lot. Okay, so what this is basically saying is essentially exactly the same equation that, and the solution it's exactly the same solution as we had before for our diffusion equation, except this time we've got m different particles. You know, whereas before we only had one person, whereas before we only had one random walk effectively, so one random walk that can either move left or right. Okay, now what we've got is we've got m different species. So if you like, we've got m different people. Got m different people, so we've got lots of different people, all kind of completing random walks at exactly the same time. So effectively, you know, we're still going to be using this equation. It's just going to be m times that. It's going to be m times that. Okay, and we can also say this. You know, we can also say a few facts about this. Well, the integration of the probability should be 1. It should be 1 fairly obviously. But now because you know because c equals m times p, so it's m lots of p if you like. So it's just like a scale factor. We've just scaled it up. We've just scaled one walk up by m different walks, and that's why we're calling it now c. So we've now got c of xt. Okay, with respect to x still, it's just going to be equal to 1 times m. So it's going to be m different walks. So this, you know, the area underneath it should no longer just be 1. It should now be m. Okay, so effectively what we've got, if for one random walk, let me just try and draw this out. If we've got one random walk, we've got this thing going on. Okay, then for, let me just try and draw this out properly. For one random walk, we've got this thing going on. Well, then for m random walks, we've got this thing going on. So in other words, it's bigger. Okay, we've got 10,000 random walkers. It's basically just a scale factor, of m, just a scale factor of m. Okay, and it's basically done by this thing. So hopefully you can kind of follow the logic and the whole idea behind it. But essentially what this is saying is that if you consider the case for one random walk, so again, it's a bit like, you know, my analogy of we kind of get the core information that we need, and then we can adapt it and build on it effectively and alter it how we need. So this is another example of this. You know, likewise we looked before where we could use the diffusion solution, the solution to the diffusion equation, and scale it up and kind of move it into the drift diffusion equation. Then we looked at the case where we could move the diffusion equation from one dimension into 2 dimensions or multiple dimensions. Now we're looking at the case where we're not just considering one random walk, we're considering multiple random walks. Okay, and it's effectively just being scaled up by a factor of m. Okay.